Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I've been walking you through the physics course. Let's consider energy quantization. This topic will be looking at energy levels of atoms. We'll consider the Franck-Hertz experiment, the types of spectra, color and light frequencies, photoelectric effect, thermionic emissions, and conclusively X-ray production. So let's begin. When J.J. Thomson conducted his experiment, he made a discovery that atoms had different particles. He discovered that atoms had charges flowing in them, even though those charges balance each other out, thereby leaving the atom uncharged. But he suggested that the charges of the atoms were scattered all over the place. So he had a diagram that included a circle and pluses and minuses all over the place. Something like that. Until Rutherford came and said no, it was wrong. And Rutherford came and explained to us that in the atom, there is a part of the atom that carried the weight, that carries the weight. And that part of the atom is the nucleus. So the weight of the atom is concentrated in the nucleus of the atom. Meanwhile, on the orbitals, we have the electrons which move around. So he suggested that this particular expression, this particular drawing, is untrue. And he came up with the one that says that we have a nucleus where we have our positive electrons, that's our protons, and we also have the orbits. We also have the orbits where our negative electrons dwell. Of course. But when Niels Bohr conducted his own experiment, he also agreed with Rutherford. But he went a step further. He said that atoms can be charged. They can exist in different stages. They can be in their ground state, that is in their natural state, or they can be in their excited state or in a charged up state. He also specified that in the charged up state of atoms, they don't just accumulate any form of energy. An atom cannot just take up any quantity of energy and be charged up like that. There are specific quantities of energy that are required for an atom to absorb to attain a particular level of excitement. Now, there is what we now describe as the energy of excitement, the energy of excitation rather. The energy of excitation is the amount of energy required to raise an atom from its ground state to a state of excitement. That is, it is excited from its ground state. We also have what we call the energy of ionization. The energy of ionization is the amount of energy required to completely remove an electron from an atom. Well, all these expressions, all these energies have their expression. And generally, we have the expression E equals HF, covering them all. Now, energy of excitement would have X here, and we also have of course, our F here is the terms energy is E, H is Planck constant, and our F here is the frequency. Our F there is the frequency. So our F also can be further simplified into V over lambda, where our V is the velocity and our lambda is the wavelength of that particular system. So let's consider other things, the Franck-Hertz experiment. But before we go into that, in a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson so far. Please answer them and we'll see you in a few. Welcome back. The other time we're talking about excitement and ground states. That is the state of excitement, that is excitation energy. And I also mentioned the ionization energy. So I wanted to give an expression and I decided to pause it to return. So what is the expression that we use in calculating these energies? Apart from the expression which I gave you earlier, which is E equals HF, of course, which can also be modified into HV over lambda. Of course, this, apart from this expression, we also have another expression, E equals EV. Now, E here still remains energy. This micro E here, that's the small e, represents the electron charge, the electron's charge, and our V here is what we describe as the potential. The potential. Now, this potential varies based on what exactly you are considering. When we're talking about the excitation energy, which is EX, excitation energy is equal to EVX. So, in excitation energy, we use excitation potential. In ionization energy, that's EI, we have EVI, where we work with ionization potential. Alright, let's talk about the Franck-Hertz experiment. In the 1900s, a lot of people were conducting different forms of experiments to discover more about electrons and their nature. And this led to a particular experiment conducted by Hertz and Franck in 1914. In 1914, in this experiment, they were trying to discover what is the nature and the amount of energy that is required to change the state of a particular atom. Of course, the setup that they used is being displayed on your screen right now. In that setup, you can see that we have the tube, a glass tube, of course. In the glass tube, of course, inside that glass tube, it is being the pressure is being reduced. Air is being extracted to create a kind of a vacuum, so that as much as possible there will be no air there, of course. And the filament, there is a filament labeled F. That filament is heated up, and when it is heated up, electrons is being released. When the electron is being released, the voltage being passed through the system helps to control the electron. And of course, it was discovered by them that the voltage passing through the system controls the speed or the velocity at which the electrons did move. So they made these observations, and from there they were able to come up with further explanation on how they were able to come up with further explanations on how to calculate the different energies required to attain a specific strata or a specific spectrum. That is a specific level in the hierarchy of excitation, whether it is in the excited state 1 or the excited state 2, or it is just on the ground level. Okay, they also came up with a description which they said that the levels of excitement can be represented with horizontal lines. It can be represented with horizontal lines, where the ground one is usually called E0, and then it increases to E1, to E2, E3, or up like that to an En. Well, so the amount of energy it requires to move from one level to another level, that is going higher, is excitation, and when you drop back, it is an emission. So that brings us to talking about the types of spectra. The types of spectra. We have two types of spectra, that is each one is called spectrum, of course. We have two types of spectra. We have the emission spectra and we have the absorption spectra. The emission spectra and the absorption spectra. Of course, in the emission spectra, ray of light or energy is being emitted from the system. This oftentimes is accomplishes the dropping of from an excited state either to the ground state or to another for excited state. That's where we usually find the emission spectra. It accomplishes the drop in states, while our absorption spectra comes up with the the atom absorbing a particular thing. Now, it could be a photon that is being absorbed. It could be a charge, it could be energy of any kind that is being absorbed. When it is absorbed, it moves from a low state to a higher state. But when an emission is being radiated, when it is the one giving out the emission, it drops from a high state to a lower state. Okay, let's talk about color and light frequency. Color and light frequency. When substances lose electrons or gain electrons, oftentimes the reaction, the loss of energy is accompanied with a flash of light. Yes, it is accompanied with a flash of light. In the krypton, when such a reaction occurs, we usually see an orange light being flashed. Of course, while such occur in sodium, we see a yellow light being flashed. An orange light has a frequency of about 606 times 10 raised to the power minus 9. The orange light has a frequency of about 606 times 10 raised to the power minus 9 meters. And of course, the yellow light has a frequency of about 589 to 589.6 times 10 raised to the power minus 9 meters. So this, you see, it depends on how much energy is being involved in the entire reaction, in the entire emission system. Either it is an emission of, especially in this kind of situation where there is an emission of light, it depends on the amount of energy involved. The energy involved can be calculated by the expression E1 minus E2, that is change in energy, equals to HF. Of course, our HF is the same thing as HV over lambda. The change in excitement. So if it is coming from a high excited state, which is E2, and it's coming low to a low excited state, which is E1, that's the change in excitement can be calculated by this expression. So we know that the frequency is dependent on the wavelength. Now, if we see a red light emission, we of course, using velocity of light, since it is moving with the speed of light, using velocity of light and Planck constant, we can determine the amount of energy that has been used up, to create that particular light. And of course, the light is being generated based on the amount of energy. That you observe that the lights also have their individual colors. Of course, we know that our extreme colors are like red. Red has a color wavelength of about 700 times 10 raised to the power minus 9 meters, and the least of the visible lights is about 450, which is violet, times 10 raised to the power minus 9, about 450 times 10 raised to the power minus 9 meters. So depending on the kind of color that comes out of it, and all this color, if you want to calculate the frequency, you can calculate it from the expression simply by using the velocity of light to divide the wavelength of the light, that is the color. All right, let's talk about the photoelectric effects. Talk about the photoelectric effects of in energy quantization. What we actually refer to is a very interesting phenomenon. It was discovered that when electromagnetic waves passes or strike the surface of some certain metals, actually light is radiated. That is, we experience some sort of emissions. Now, these emissions vary depending on the kind of nature of the material, that is, the metal in question. For sodium, very little light of UV lights, that is ultraviolet light, is being radiated, which may not be seen. But for serious bigger atoms like cesium radiates light as high as ultraviolet, infrared, the infrared lights. So it was being discovered that there is an amount of emission that comes out, and for this emission to come out, a particular expression should be used to explain what is happening there. We all know already that the energy involved in liberating an atom, that is an electron, from the system is calculated with VEO. Of course, that's the potential to release the atom. Yes, where EVO, that is our E, energy, equals the charge multiplied by the potential of releasing this particular electron. So this also can be related directly to the force with which the should I describe it as now the electron striking the surface, or the light being used to displace this electron. So that force can be calculated as, it is a kind of kinetic energy, so it is half mv squared. So that expression exists for the system. We can use half mv squared, that is knowing the mass of the electron, knowing the speed at which it is moving. Of course, it's definitely related to each other because that is already energy on its own. Now, for the photoelectric effect talks about the possibility of us removing an electron with the use of a wave. So if we have a wave medium and we can discover how much energy is being input into the system, of course, for the wave medium, it is easier for us to work with wavelengths and frequencies. So we have the expression coming up again. Our E equals our Planck constant multiplied by our frequency, which is also equal to Planck constant multiplied by velocity divided by the wavelength. Of course, the wavelength and the frequency here is what we describe as the threshold frequency. The threshold frequency, and threshold frequency is always linked to the threshold wavelengths. So what do we mean by threshold frequency? The threshold frequency is the frequency which is the max, that the maximum frequency. Threshold frequency refers to the frequency which is the minimum frequency required to displace an atom or an electron from its original position. Is the minimum energy, minimum frequency at which an electron can be displaced from its original position. So these conditions must be met for us to have it, and that simply explains the thermoelectric effects, the photoelectric effects of energy quantization. But even at this, when we now consider the entire system, we discover that a certain amount of work must have been done. So we use our file, that is this, to represent the work done in displacing the electron, the work done in displacing the electron. So at the end of the day, we have our formal equation, because of course some energy has to be used up, some work has to be done. So we use this to represent our work function. So our E, which is total energy possessed in the system, for anything to happen must be equal to HF minus work done function, that is work function. All right, let's talk about thermionic emissions. Thermionic emissions. When we say thermionic, what does it suggest? The word thermio or thermo suggests that it involves heat. Yes, it involves heat. We can also use heat to bring about emission of substances, that is emission of waves, emission of radiation, emission of electrons, even from the atom. So this talks about heat-related emissions. It has to do with heat-related emissions. Of course, we know that heat has certain metals have the possibility or have the tendency of losing their electron, their freest electrons to heat. So because of this condition, we have to put together everything that we can put together on heat production, on the effect of this heat on the energy system. When we consider the energy system of this kind of substances, we discover that E, which is the amount of energy required to displace an electron, equals EVO. Of course, we've been working with this for a while. And also, the electron that will be displaced must be the electron that will be displaced must be struck at a particular velocity. So we know that it is going to require kinetic energy, which is half mv squared. It's going to require a certain amount of kinetic energy to displace this electron. So at what speed or at what velocity must this electron be struck? So to calculate that velocity, we simply collect our like terms, and we have v squared will be equal to 2 EVO over m. So v will be equal to the square root of 2 EVO over m. So this is the formula, the expression for calculating the velocity at which the surface of the metal must be struck by either light or the source of emission, the kind of the emission that is coming to liberate the electron from the metal. Let's discuss X-ray. X-rays. So what are X-rays? X-rays are electromagnetic rays. They have no charge. They are not sensitive to magnetic or electrical fields. They are not sensitive to magnetic or electrical fields. In fact, they are almost unstoppable. They do not diffract. They can go even into metals, as they can penetrate lead even to certain centimeters of lead before they can be stopped. They are very, very fast. They move on a very high frequency, and they have very, very short wavelengths. They are very, very short wavelengths. So what are the advantages? What are the uses of X-rays? Yes, we'll still be talking about X-rays later in this class, but let's look at one or two things. X-rays are used for taking images of internal organs of people. Since due to their penetration, they can be used to take internal organs, images of internal organs, interior parts of people, like our X-rays that we used to take pictures of our bones and all the other things like that. X-rays also can be used in the treatment of certain diseases such as cancer, and also for regulating the activities of certain life tissues. In this lesson on energy quantization, we'll consider the energy levels of atoms. We looked at the Franck-Hertz experiments, the types of spectra, color and light frequencies, photoelectric effects, thermionic emissions, and X-ray production. In a few seconds, some questions will be displayed on your screen to test your knowledge of what has been taught in this lesson. Please answer them, and if there is any part of the questions, any of the questions that is giving you that is proving to be difficult, you can go over the video one more time for clarity on such area. Thank you.